Hello, my name is Tsabedze, and I will be presenting the work done with Eric Hartman, Brennan, and Professor Zhang. Authors are from the University of Nevada, Reno. Our work is titled A Compliant Robotic Wrist Orthosis Driven by Twisted String Actuators. Before we dive right in, here is an outline of the presentation. I will give an introduction to robotic wrist devices and motivations why our work is essential. I will then talk about our project goals and why twisted string actuators were used. I will then further give the design considerations, how we use and why we use supercoiled polymer strings, and then talk about the choice of motor placement. I will then spend some time talking about the characterization of the orthosis before talking about the discussion and the plan for future work. Robot-assisted wrist rehabilitation has been in development for the past 3 decades or so. The research has highlighted several main advantages of using robotic wrist devices for rehabilitation. Firstly, these devices provide accurate dynamic routines compared to human-led rehab. Secondly, since these devices rely less and less on physical therapists, they reduce their workload. This means they are able to focus on patients that might need much more hand-holding. Thirdly, getting access to performance metrics is so much more efficient and straightforward. Examples of commercially available wrist orthoses are the Power, Wrist Robot 2.0, and Dynasplint. In spite of all these advantages, wrist rehab is still an open research area due to these devices still containing some major limitations. For a start, when direct drive motors are used for actuation, it is possible to actuate all the degrees of freedom of the wrist. However, most often than not, these devices are bulky, rigid, and attached to tabletops. Soft fabric-based pneumatic actuators have shown it is possible to design compact, wearable wrist devices that are comfortable to wear. However, SFPAs also tend to have limited actuation of the wrist. Furthermore, the need for a pressure source means that they are tethered. Emerging artificial muscles like supercoiled polymers or shape memory alloys have been used in wrist orthosis, providing wearable and untethered devices. However, as seen in the devices on the screen, these devices have limited degree of actuation of the wrist and can also be bulky. Keeping the motivations in mind, the goals of our projects were twofold. First, to design a compact, compliant, wearable wrist orthosis that is capable of actuating all the degrees of freedom of the wrist. Second, to characterize the performance of the device and show that activities of daily living can be achieved. Before going any further, it is important to talk about the choice of actuation mechanism and why it was selected for use in this work. Firstly, twisted string actuators are compliant artificial muscles that convert rotary motion of electromagnetic motors into linear motion through the twisting of two or more parallel strings. As shown from the video, the direction of travel is parallel and in line with the motor placement, and the amount of load can be fairly high. TSAs provide several advantages compared to other actuation mechanisms, like direct drive of motors. TSAs provide a high force amplification from low torque motors. This means that massive high gear ratio motors to provide high torque are not a need. This leads to a smaller footprint and a compact form factor. This force amplification means that TSAs works well where compactness is desired. Since TSAs use strings, they are more compliant compared to rigid gears in the direct drive actuation. Due to these desirable properties, TSAs have been used in wearable robotic devices like forearm assist, assistive glove, and assistive hip joint exoskeleton. As seen from the video shown earlier, TSAs require the twisting of strings in order to actuate. This need makes embedding strings into soft sleeve difficult. Directly embedding strings will increase the friction. Further, Having the strings directly embedded and in contact with the user's skin would cause irritation during twisting. To minimize friction and skin irritation, we used a flexible tube. This tube decoupled strings from the sleeve but did not sacrifice compliance of the device. Now that I have talked about the motivations, goals, and the choice of actuation mechanism, let me introduce you to our wrist orthosis. Our device uses 6 TSA units arranged in antagonistic fashion to achieve flexion extension, adduction abduction, and pronation supination. 4 of the TSA units utilize stiff strings. These TSAs actuated the flexion extension and pronation supination degree of freedoms. 2 TSA units use compliant supercoiled polymer strings for the actuation of the adduction-abduction degree of freedom. Lastly, we show that there are 2 motor placement configurations that can be achieved with this device. I am going to show you a video of the device actuating all the wrist degrees of freedom of an anatomically identical prosthetic arm. It is important to note that using the prosthetic forearm makes it easy to decouple the motions of the wrist. Now the question to answer is why are supercoiled polymer strings used for some TSA units? Well, SCP strings provide 2 key merits. Supercoiled polymers are made of compliant and conductive nylon thread. The compliance of the SCP strings further increases the compliance of the TSAs. In addition, since they are conductive, SCP strings allow for position sensing, removing the need for an extra sensing unit. SCP strings were chosen since our lab has extensive experience working on SCPs. While the compliance is important for wearable robotic devices, too high compliance may reduce the force output, and if it is not repeatable, use in dynamically changing force requirements cases will be affected. Therefore, it is essential to characterize the amount of compliance, repeatability, and the amount of force output. To characterize the compliance of SCP strings, the following setup was used. In this setup, a position sensor was used to keep track of the stretch of the SCPs as the load was increased and then decreased. First, it is shown that loading and unloading the SCPs returns to a similar position, showing the repeatability of the stretch. Second, increasing the diameter of the strings increased both the load output and the stretch. As can be seen in the figure at the bottom, the stretch ranged from 15% for the 5-ply to almost 45% for the 20-ply. With this device, we were able to use 2 motor configurations on the forearm. These configurations use the same number of motors. In the single motor actuation, the motors are located at the midpoint of the wrist for the abduction, adduction, and the flexion extension axis. And in the double motor actuation, motors are slightly offset from the midpoint of these axes. It is noted that the single motor actuation was used in this work. Further, the choice of motor configuration does not affect the placement of the pronation supination motors. As mentioned, in the single motor actuation, motors M1 through M4 are located at the midpoint of the flexion extension and the adduction-abduction degree of freedom. The first 2 pictures from the left show the side view of the forearm, where M is the motor and A is the attach point. The schematic to the right shows the top view, and when M4 spins clockwise and M1 counterclockwise, the upward motion is achieved. The middle figure helps show the side view as well, showing the upward motion. In the double motor actuation, the motors are slightly offset as shown in the schematic to the left. The top view and the side view show that when M4 and M3 spin clockwise and M1 and M2 spin counterclockwise, the outward motion is attained. The choice of motor placement affects the force produced by the motors. Single motor placement produces less force output. If single motor placement produces enough force for activities of daily living, double motor placement will always produce higher force output. To characterize the performance of the orthosis, the range of motion of the device was measured, both when the device was connected to a prosthetic arm and also when a healthy subject was wearing the device. The range of motion starting from neutral to positive and then from neutral to negative was measured for all degrees of freedom. Further, it was measured starting from maximum flexion to maximum extension, with similar measurement performed for the abduction degree of freedom. These range of motions are comparable to those needed for activities of daily living. In addition, we showed that the device can actuate for a healthy subject without muscle activity when the device is actually on. When the device is not engaged, muscle activity can be seen. But when the device is active, there is no muscle activity. To conclude, we have presented a compliant, compact, wearable orthosis that activates 3 degrees of freedom of the wrist. The performance of the device for range of motion was characterized. For future work, a closed-loop architecture for synergistic coupling of the 3 degrees of freedom will be studied. Furthermore, extensive human experiments will be performed for functionality and comfort. Thank you. Please take a look at our paper for more details.